So yeah, we're happy to have Romain Vasseur from UMass Amherst. He's going to talk about superdiffusive hydrodynamics in isotropic spin chains.
All right. So yeah, thanks a lot for the invitation. It's great to see everybody. Although I wish I could use this opportunity to visit California, but hopefully soon. All right. So today I'd like to tell you about some recent work on superdiffusion in isotropic spin chains. Basically I'll try to just give you a flavor of what the problem is, why it was uncovered only very recently, and why I think it's cool and interesting and a lot more robust than we thought, at least a few years ago. So before I start, let me thank my collaborators on this, in particular my postdoc, Braden Ware, who will soon be moving to Maryland, my long-time collaborator on this, Sarang Gopalakrishnan, and more recently, Jacopo Denardis and Nene Ilievski. So everything I'm going to tell you is also based on discussion with many other people, including ongoing discussions with people in the audience. Okay. Cool. So, all right, let me start by kind of just setting the stage just to make sure we're all on the same page. So I'm going to be talking about a relatively old school topic in some way of condensed matter physics. I'm going to be talking about transport. Okay. Just to set the stage, you have different ways you can think about transport. So here in this talk, I'm going to be thinking of a 1D system, more precisely spin chains in general. You can imagine your system is going to be coupled to, say, reservoirs on the left and on the right. Can you see my cursor, by the way? Yes, no, okay. All right, so yeah, it's, your spin chain is going to be coupled to like reservoirs, and, on the left, you could have different temperature, different maybe magnetization. So here in this talk, I'll be thinking of spin transport. So, you can imagine you have like a gradient of magnetization or field, and, you wait long enough and you'll have a current flowing in your system, and that will characterize transport properties of your system. An equivalent way to think about this is within linear response regime is to imagine you have a tiny perturbation somewhere in your system, like a tiny spin or energy perturbation, and you look at the way it's kind of spread with time, right? And so there's a typical scaling of position, so the width of that perturbation with time that defines a dynamical exponent z, right? And so that dynamical exponent can be different for different conserved quantities you would have in your system. Okay. And so just to remind you, what do we expect in general? Well, on very, very general grounds, just based on hydrodynamics, we expect just kind of broad universality classes. So the most important one is the one we learned about, very early in physics, which is diffusion. And we have Fourier's law, Fick's law, right? Where the current would be proportional to the gradient of the conserved quantity that you have. That's kind of that's the most generic scenario, right? So in a gradient expansion, that's like the leading order. It corresponds to the familiar case where you have a finite conductivity, and it corresponds to a dynamical exponent 2 in that equation here, right? So the perturbations spreads the square root of time. Okay, so that's the natural case, and it's the one we all know and love in some way. And that's the one you should expect in most systems, quantum or classical, right? So another kind of generic universality class that we're also familiar with is ballistic transport, right? So this one is dynamical exponent 1. It usually requires some symmetry or some extra ingredient to be stable. And it corresponds to having a Judo weight, so say a delta peak in your conductivity and dissipation less transport. Okay, and so anything in between those two universality classes is generically something I'm going to call anomalous diffusion, in that it's unusual and will not fall in those categories, right? And so you can have subdiffusion, where z would be larger than 2. So say near the MBL transition is one example in 1D, and superdiffusion, which would be somewhere those two cases. Okay. All right. So So now that we have like those basics, let me kind of tell you the main say the main claim. So this was discovered just a few years ago. So this paper here is really the one that kind of triggered this whole field I'm going to tell you about. So it's a relatively simple story or simple claim. So you just take one of the simplest Hamiltonians in 1D of magnetism, just a Heisenberg XXX Hamiltonian spin 1/2. Okay, doesn't get any easier than this. Antiferromagnet. It doesn't really matter. You could take a ferromagnet as well. And the claim is that actually spin transport in the system is super diffusive. Okay, and it actually has this exponent 3/2, that I defined in the previous slide. Okay, and so those people from the Ljubljana group realized this numerically. So this is some MPO plot. Okay, so this is space, this is time. They start from some initial state where you kind of have a domain wall, where you have higher magnetization on the left than on the right. Okay, this is a mixed initial state, so it's actually at very high temperature. So it's not, so it's finite temperature transport. And they had very good numerics. They could go to long times, and they realized this actually has this anomalous exponent. Okay, and so when this result came out, I think many people, including myself, were very surprised. And there are many reasons to be surprised, because this is such a well-known model. Like, you would think we would know everything there is to know about the Heisenberg antiferromagnet, right? And it's spin transport. It's not like some exotic, it's not some super exotic observable, right? At low energy, it's a Luttinger liquid, Anyway, you would think we would have realized this by now. And somehow, those people realize, well, there's a big surprise here. Okay. So there's been a lot more numerical studies on this. I'm not going to quote them all. Here I'm showing just some other type of data. It's been confirmed by many groups by now. So this is showing some time-dependent diffusion constant, if you want, and here you see it grows with time. And it's true at any temperature, right? And here this is spin 1/2. This is a spin 1 chain, okay? And it looks pretty similar. I'm mentioning this right away because the spin 1/2 chain, as you might know, is integrable, right? So it has all those conserved quantity. It's very special. The spin 1 chain isn't. Okay. And if you look at the plots, it looks fairly super diffusive with this power. So here it's t to the 1/3. So it's the same exponent here. Okay. So shortly after this, people really pushed the numerics and realized it's not only an exponent like we have.
I'm so sorry. Can I ask
go ahead.
quick questions? I'm sorry. I guess just to make sure I remember, I actually don't remember this. So in these two cases, for the spin 1/2 Heisenberg and spin 1 Heisenberg, you're saying that the spin transport is super diffusive in both cases?
Well, numerically it is. So you'll see later on in the story, I'll argue it's actually super diffusive here. And here we expect it actually crosses over to diffusion, but probably on a time scale we cannot access. Right?
And these are all at very high temperature?
Yeah, so you see the temperature here. So it ranges from 0.5 to 10. So it's a broad range.
And can you also remind us, if I did the same plots over like the same timescales and I was looking at the transport of energy, what would I see in these two models?
Purely ballistic for spin 1/2, and you would see diffusion for spin 1.
Okay.
So that's it. I haven't seen the numerics for spin 1. I know what happens for spin 1/2, but I would expect diffusion for spin 1, but maybe it shows some ballistic-ish things.
So at very late times, if you could access it, you'd expect for spin 1/2, energy is ballistic, but spin is super diffusive.
Correct.
And at very late times for spin 1, both are diffusive, but if you can only access short times, you might see super diffusion.
You see super diffusion. So yeah, that's going to be actually the claim of the talk. Okay. Yeah. So but at least numerically, those things look pretty similar, I guess. Okay. So there will be a difference between those two cases. But
thanks.
So if I could, what is the crossover point? What marks crossover?
Okay, well, let me get back to this because that's pretty much the whole talk. Yeah, that's my whole talk. Yeah, so I'll get to this. I'll talk about it.
Well, maybe one subtle question then. So, how does the prefactor change between these two scaling regimes?
I'll talk about the prefactors. Yeah, let me get back to those
Okay,
questions.
you're getting
again.
it.
But yeah, don't worry. I'll talk about this. Yeah. Cool. So great. I'm glad there are so many questions already. Cool. So let me keep going a little bit. So my goal will be to kind of give you a flavor of how we understand this, and in which cases it's stable and which cases it isn't. Let me mention that it's not only an exponent we have, like numerically, again, the same group kind of showed that it appears to, this whole spin transport appears to fall in this celebrated Carda-Parisi-Genk universality class, KPZ, okay, which is a celebrated universality class of non-equilibrium physics in classical systems. It was introduced in the context of surface growth, nothing to do with spin transport. So that is to say, like if you look at correlation, dynamical correlation functions, the scaling functions, which would be a Gaussian if you had diffusion, here is not, or regular diffusion at least, right? So here is another type of function, which is in this KPZ class. And it tells you there's some kind of emergent hydrodynamics in some way in the system, which is very unusual. And this is something we actually don't really fully understand yet. So as I'm just stating results for now, let me also mention that there was a recent experiment. This was published pretty recently. So this is from an actual solid state system. I expect we'll see other experiments in the future, in particular in cold atoms. So this was a neutron scattering experiment in this quasi 1D material, where they show that pretty high temperature, I actually truncated the figure, they go to even bit larger temperature than this, that in some regime where they have low enough frequency, the structure factor scales with that exponent, which is very near 1.5 and is quite far from both diffusion and ballistic. Okay. And so finally, let me mention that by now we have a lot of evidence that this is not just the Heisenberg chain, and it's kind of a super universal phenomenon in some way. Okay, so we had a paper calling this super universality of superdiffusion. So basically, if you take many systems, all those systems are actually integrable here with various symmetric groups that are non-abelian. They all obey this kind of superdiffusive transport. Okay, so this is a numerical plot. So this is showing the width of like a perturbation versus time. This is showing return probability. And the dashed line is what you expect for this exponent 2/3 or 3/2. Okay. All right. So, okay. So let me summarize what I've told you so far. So this is just, I haven't explained anything. I've just given you, what we seem to observe from numerics and experiments. Is that apparently there's really superdiffusive transport in this celebrated Heisenberg spin chain and in a very large class of quantum chains. Okay, anything with a non-abelian symmetry. So the Fermi-Hubbard model, okay, in particular, for any U, will have charge and spin transport that are superdiffusive. Okay, so that's a claim that's especially relevant for cold atoms, right? But again, you would think we would know this, but no. Okay, and so what are the key ingredients? So what we seem to know, at least from, again, numerics, is that we need some kind of non-abelian symmetry, like a spin rotation SU2 symmetry or something bigger. So how do we know this? Well, if you break that symmetry numerically, you see immediately you lose this superdiffusion. You either get ballistic or diffusive transport. Okay.
So I'm super sorry, Romain. Can I interrupt
for
go ahead.
One
more question? Just to make sure, in the Fermi-Hubbard case, that's in any dimension, or is that restricted to 1D?
No.
Or
no? So it's going to be a very 1D phenomenon, though. Yeah.
So all of this is there's no example of this that's known in dimension higher than 1, or there is.
I mean, you can have different things in. So in 2D, there was, I think you get diffusion. I mean, there was also this experiment from Martin Zuerlein's group, right, where they did this, and I think they measured the diffusion constant there. So I expect in 2D it should be diffusive. I mean, you can have different ways you could get anomalous transport, but not really based on what the story I'm going to tell you about. Yeah.
Thanks.
So 1D, yeah, I should have had this actually in the list of key ingredients. It's 1D. So you need 1D physics. You need spin rotation symmetry. And so the last ingredient is that, okay, integrability seems to play a key role. So, that may contradict a bit the plots I showed you, right? Because I told you, all right, you have spin 1/2 and spin 1. So, I mean, we do observe superdiffusion in non-integrable models, but we do have examples of systems where you have a non-abelian symmetry and you get regular diffusion. Okay, and for those of you who are curious, if you take a random unitary circuit with SU2 symmetry, you can easily show that spin transport is diffusive. Okay, so at least we have counterexamples of, that it's not enough to just be 1D and have SU2 symmetry.
Romain,
and so
maybe a comment and question. So it's also known that classical Galilean invariant systems have KPZ transport, and it seems like this might be related. Is it?
Good. Thanks, Ehud. I should have mentioned this. So I should say, like in the first point, this is also observed in classical spin chains. But you're right. So here, of course, I don't have Galilean invariance. So for those of you who know, like in 1D, if you take a Galilean invariant system, hydrodynamics is anomalous in 1D, and you have this theory of nonlinear fluctuating hydrodynamics that predicts that you have KPZ broadening of the sound modes. So here I don't have Galilean invariance, and I don't have any ballistic modes moving around. So that's a difference. So there is actually no relation, at least that I understand or that we know of. So here it's not like KPZ broadening of a sound mode that's moving ballistically. It's really like, the whole transport is KPZ. But you're right.
You could maybe imagine that there are ferromagnetic spin waves are sort of Galilean invariant.
Well, I mean, so you'll see. I mean, so maybe there are connections we don't fully understand. Let me put it this way: you'll see there'll be like actual ferromagnetic Goldstone modes in the rest of the story. So
okay.
But yeah, if there's a connection to this, nonlinear fluctuating hydrodynamics, we don't really understand it at this point.
Mm-hmm.
Cool. So let me get going and tell you a bit about how we understand this. So in the next few slides, I want to give you a flavor. So my strategy is basically give you a flavor of how we understand this, and I'm going to start with this Heisenberg chain, which is integrable, and then I'll talk about the most interesting question, which is what happens when you add perturbations and why it's more robust. It seems to be so robust. Okay. So the framework that I'm going to use is known as generalized hydrodynamics. You don't need to know anything about this because I'm actually not going to need anything from it, but just so you know the name. Okay, so it's basically a hydrodynamic framework for integrable systems, right? So this Heisenberg chain with spin 1/2, it has all those kinds of quantities. And equivalently, you can think of it as a kind of kinetic theory approach for the quasi-particles of a system. And that's kind of the most important here. So basically, the spin 1/2 chain Heisenberg has stable quasi-particles. Okay, so quasi-particles are, of course, familiar to all of us in quantum matter physics. And here, integrability kind of makes them infinitely long-lived. So basically, you can kind of write a Boltzmann equation if you want for those quasi-particles. All right, so let me give you a flavor of how we understand the superdiffusion. How do you get superdiffusion here? So the key will be to understand the quasi-particles of this system. Okay, and so even though I said I was thinking of an antiferromagnet, I'm actually going to think of a ferromagnet. And because those are actually the nice quasi-particles that are preserved by integrability. So let's say you're doing like regular, again, ferromagnetic physics. So say you have a ferromagnet, a reference state where all spins point in the same direction. So, the nice quasi-particles of a system will be, say, a magnon, say a spin flip, right? In some cartoon way, which will look like this, we'll have spin 1, right? And you can also have bound state of magnons, and they are called strings. Okay, so those can exist in other magnets, right? What's special about the spin 1/2 the spin 1/2 Heisenberg chain is that those are actually stable even at infinite temperature. Okay, and so even if you take an antiferromagnet, actually those are the nice quasi-particles one should think about, at least from the point of view of integrability. So it's a bit counterintuitive, but they end up being stable. And so the claim is they behave like nice semi-classical particles. Okay, so meaning they don't they kind of interact with each other, but they only dress, there's some kind of dressing by interactions. But otherwise, those guys don't backscatter or anything like this. So say you have, you have those magnons and bound state of magnons, and I'm labeling those bound state of magnons by a quantum number S, that goes from 1 to infinity. Okay, so you can have bound state of like 100 magnons that somehow are stable in that system. Okay, which of course would not really happen in an ordinary magnet. Okay, so they have infinite lifetimes, and they move with some parameters you can compute from Bethe and Zat's things that I'm not going to detail in any way. So for example, in a thermal state, we know the density of those guys, we know their velocity, and perhaps the simplest thing is we know their magnetization or spin. So this last one should be intuitive, right? A magnon has spin 1, a bound state of 2 magnon has spin 2, bound state of 3 magnon has spin 3, and so on. So the spin they carry is S. Okay. So this has been known for a while, right? You have all those quasi-particles in those systems. So, the reason this is still puzzling is, you have ballistically moving quasi-particles. So quasi-particles move with the velocity, right? So you have a gas of those. If you take a finite temperature state, you have a gas of those guys. They move ballistically. They don't backscatter. They don't interact in any fancy way, right? They're already dressed by interactions, if you want. And they are charged, right? So of course, if you have like ballistically moving quasi-particles that are charged, you expect ballistic transport, right? And actually this one-line argument is why like transport in integrable systems is almost always ballistic, right? So if you take energy transport in that system, for example, it is ballistic because you have those quasi-particles moving around and they carry energy, okay? So, well, that doesn't really explain why you have this superdiffusion then, right? And so we have one more ingredient, which is really, I think, the key physics here, is some physics of screening. Okay, and again, it's not something that's like very new to integrability or anything like this, right? So think of a magnon that's moving in a ferromagnet where you have like domains of spin up and down, right? So think of a ferromagnet at low temperature. You have those domains of up and down. And think of a magnon. So here I'm drawing a magnon, which is a spin down, moving in a sea of spin up, right? And think of it moving semi-classically, kind of hopping to the left here, right? So you have this magnon, which is spin down that moves around. And now think about what happens if it collides with a big domain of spin down, which in my language is like a bigger quasi-particle. Okay. And actually what happens is that it goes through, but it kind of flips signs, right? So you have like a flip-flop exchange here. And now you have a magnon, which is a spin up that's moving in a domain of spin down. Okay, so this is kind of a known effect. You can convince yourself it's always, you think of it purely semi-classically, right? So you'll have a magnon that just move with the velocity. It's a spin down in a majority of spin up, and then it will get converted as a spin up in a majority of spin down. Okay, and so as a result, if you think really of the charge that it carries, right, it's going to oscillate. Okay, so it oscillates between spin 1 and -1. So effectively, its charge as it moves in a big system will effectively go down to 0. Okay, so we say that it's it's getting screened, and really that's the main physics of the superdiffusion. So you can do like a back of the envelope calculation of how long it takes for a quasi-particle to be screened. And so here this generalizes to like all those quasi-particles. They will, once they collide with a quasi-particle bigger than themselves, they will start to get screened. And we know the density of all those guys and we know their velocity. Okay, and so from this we can get a screening timescale. So you have those quasi-particles labeled by S and they'll be screened in this way. And so this very simple physics actually is the whole physics of the superdiffusion. So only at a given time, only quasi-particles that are big, that with this label that scales with time in this way contribute to transport. And the reason is like quasi-particles that are smaller than this, they are fully screened. Okay, so they're basically neutral and they drop out of the problem. So say you have a spin 1 magnon, it has collided with many bigger domains and it's fully depolarized and it's completely neutral. And quasi-particles that are much bigger than this, well, they move very, very slowly and they're very rare. So because of, the density decays with S and the velocity decays with S as well. So there's kind of an optimal S that scales with time. This 1/3 is really the same as the 1/3 in the diffusion constant versus time. Okay. So you can plug all of this in kind of a Kubo theory thing, which I'm going to skip because it's not that interesting, and you get superdiffusion out of that, right? But that's really entirely the main physics is like those quasi-particles moving around. Sorry, that gets screened, and this and the fact that you have those bigger and bigger quasi-particles that contribute to transport, and that gives you the superdiffusion. Okay. So you can plug this into a Boltzmann type equation formalism and do a bit more math, right? But that's really the main physics. So, all right. So now I'm gonna, the last thing I want to do in this talk, and which is probably the most interesting one, is to kind of understand why this is stable. Right? Because I had those quasi-particles that are stable. So in recent years, we've spent some time understanding what those big quasi-particles are. So I say big because when T is large, when T is large, S is big as well, right? So you get those big bound states. And they don't look exactly like the cartoon I showed you. What we realized, and that was pointed out first by Vilchandani, is that those big quasi-particles, they actually look a bit like Goldstone modes. They're kind of soft-like excitations. So they look like this picture. This is an actual plot of what this looks like. So we call them Goldstone-like solitons. So they're solitons because they move ballistically, right? They're quasi-particles. But if you look at a spin texture, it's kind of a soft excitation here. So it has very low energy, right? So if you have actually the energy of those guys of size S is 1 over S. Okay, so they're very slow, like vacuum rotation. Okay. And this is going to have a key role actually of why this is stable to a large extent. Okay, so in the last 5 minutes that I have or something, I want to address what I think is the most interesting question of all of this. Is why on earth is this stable, and why do we see this in spin 1? Why do we see this in experiments? Right, I mean, this solid state system certainly has many things that break into gravity. There are many other features here.
Come on, can I ask one more question on the previous?
Yeah, please do. No, yeah.
So I just want to get a sense. So somehow, so we've been focusing. I mean, you mentioned these two things. One, which is super diffusion with this z = 3/2 exponent, and then you've also mentioned this, KPZ universality class.
Yeah.
I just want to get a feeling. I know they're not exactly equivalent, but is the general feeling or the general gist that whenever you see z = 3/2, more or less it has to be KPZ? Or I mean, is it it's hard to get something that's not KPZ if you have z = 3/2, or are they equivalent in spirit or not?
Yeah, it's a very good question. So they're not equivalent. I mean, that said, there are big universality classes. So 3/2 smells a lot like KPZ. Let's put it this way. But so to this point, let me say we understand the exponent 3/2 very well, but we don't understand KPZ very well. So there is an argument by Veer from this Goldstone mode picture that allows you to kind of understand maybe why you have KPZ. But there are several gaps that have yet to be filled. So I think the short answer is we don't really understand why it's KPZ and not something else. It's something we see from numerics. It seems to be true. What we really know for sure and understand pretty well, I would say by now, is that exponent 3/2.
I see.
So it's still an open problem. We don't, it's maybe related to Ehud's question of how this relates to this KPZ and maybe Galilean invariant system.
So even for the simplest example of this spin 1/2 quantum Heisenberg magnet, you can't prove that it's KPZ?
No, we don't know that. We can, we understand many things. We can compute the superdiffusion constant, the prefactor exactly, and things like this. But we don't understand why it's KPZ, I would say. I mean, again, there's some argument by Beer, I should say, there's a proposed theory on this, which I think has some parts. So it's not fully complete. There's some there's some reasons to expect that it's probably KPZ.
Okay.
But
right.
I think, yeah.
Thanks. Sorry.
Yeah, it's okay. Great. So right. So the last thing I want to tell you in this talk, and again, it's kind of the most interesting part. So hopefully you're all still awake at this point. So it's why is this stable, right? So I showed you those plots, saying you have spin 1/2, spin 1, and it looks super diffusive. this one is not integrable, right? So the whole theory I gave you doesn't apply. Again, we see this in like experiments as well. And I should say, so, you think, why is that so, right? So maybe you should think it has nothing to do with integrability. But here I already mentioned like random circuits, for example, with SU2 symmetry, which do not have superdiffusion. You can also think of doing hydrodynamics for SU2 systems. So this was done by Paolo and collaborators. I think I saw Paolo in the audience. And it gives you vanilla diffusion. So you don't get superdiffusion out of this as well, right? Okay, so what happens if you break integrability? So that's something we started doing pretty recently. Well, so from the picture that I gave you, quasi-particles will decay. They'll have a lifetime. Okay, so all those nice quasi-particles won't be long-lived anymore. And we can have a Fermi golden rule estimate of how they'll decay. If you take a generic perturbation that breaks SU2, you can quickly convince yourself that this rate will either be order 1, or if anything, it will scale with S. So meaning those big quasi-particles will decay very quickly. Okay. And so as a result, this whole story that I told you goes down the drain and you get diffusion. Okay, and so we've checked this numerically. So for example, we took like this Heisenberg chain, we added noise that say couples to SZ, something that breaks SU2. And this is numerics showing the time-dependent diffusion constant. So I'm kind of skipping how we measure this. But for different noise, so gamma here is the strength of the noise, and you see it goes to a constant. Okay, so we get very nice diffusion constants, I should say. So that's maybe the nice thing, but it's still diffusion. Okay, so all of this story goes away. But here comes like the more interesting part. So like if the perturbation preserves SU2, or it preserves spin rotation, those quasi-particles that lead to the superdiffusion are long-lived. And the reason they are long-lived is because they are like kind of Goldstone mode-like. Okay, so the reason you can understand this is, let's say like those big quasi-particles, so they'll slow vacuum rotation, right? They look like Goldstone modes. If you try to act with something that preserves spin rotation, its matrix element is going to be strongly suppressed, right? By definition, this, it's a soft excitation, right? So it's a slow vacuum rotation. So anything that preserves spin rotation symmetry is going to have near zero matrix element acting on those guys. Okay, so that's basically Goldstone physics. That's kind of the definition of a Goldstone mode, right? You have a soft, low energy excitation. And so because of this, you can actually argue, again, in the Boltzmann equation type of framework, that at least perturbatively, this whole phenomenon that I told you about is stable. That is to say, if you put a perturbation, you put Fermi golden rule, you compute the lifetimes of those excitations, actually, those very, very big quasi-particles that are responsible for the superdiffusion are very long-lived, okay? And their lifetime is actually asymptotically infinite for the biggest ones, okay? And so, and we check this numerically, okay, so it's relatively short times, but still, we did Heisenberg with next nearest neighbor, with staggered couplings, anything you want. This is a diffusion constant versus T to the 1/3. It's nowhere near saturating any, in all the numerics, the timescales you can reach, this is still increasing. So we see this superdiffusion in all those non-integrable cases. And so this is on the right here, it's like a dynamical exponent extracted, going to longer times and being optimistic about MPOs, but, and it's still compatible with 3/2. You see it's very far from diffusion.
Romain, if they're infinitely long-lived asymptotically, why do you say it's not the asymptotic universality class?
Just because it's second-order perturbation theory.
Okay.
So we don't know, that there may be higher-order things we neglected.
So, but is it a question or
it's a question?
We don't know it's going to be diffusive.
Well, I mean, I would okay, my personal belief is that probably it's diffusive because, again, SU2 alone is not enough to give you superdiffusion, and when we have those random circuits. So within this Boltzmann equation framework, the answer is if you do Boltzmann equation, you put a collision integral that comes from Fermi golden rule, superdiffusion is stable.
Wait, but in random circuits there is no energy conservation. So maybe that's so you can take these, for example, Boltzmann treatments and add some noise that breaks energy conservation, and then you'd probably kill it immediately, right?
So actually, yeah. So we did that. So that was my last slide, actually. So we also did that adding noise. We can still do this perturbatively here. Energy is not conserved. And so because of this, your kind of phase space is a bit different, right, of the perturbations you can add in your Boltzmann equation. And here, like the Boltzmann equation framework that we have predicts almost diffusion, but with a log correction. So it predicts like a conductivity that averages logarithmically.
Mm-hmm.
And we did numerics, and this is D versus log T for different strength of noise. And you see for small noise, it's a pretty good straight line. However, if we crank up the noise, you see it looks like it's saturating.
Okay,
so we have some evidence that, this is really, we're doing a perturbative treatment. So there's probably some non-perturbative physics over there, or at least higher order in perturbation theory that we're not taking into account. So we have some evidence here. I think if you crank up gamma even more, you really see it even more clearly that it's saturating. Does that answer your question, right? So
yeah. What if you replace energy conservation by another conservation law, like couple it to a charge, another conserved charge, and do a random unitary circuit? Maybe you can stabilize it then.
Yeah. So the inset is actually this. So this is coupling to a higher order. This is coupling to energy current, which is also SU2 invariant. And so we haven't checked everything, but it's it still looks like it's saturating. So let me just wrap up and maybe take more questions. So hopefully I've convinced you that there's some kind of anomalous and unexpected, superdiffusive transport and integrable chains, at least, right? Isotropic chains. Hopefully I've convinced you there's a relatively simple mechanism based on this screening. Integrability plays almost no role. It's there, to stabilize those quasi-particles, but otherwise it's basically a simple kinetic or Boltzmann equation explanation, right? It could be about just ferromagnets in general. You really need integrability only to stabilize excitations. Perhaps really the surprise of the last year is that all of this seems to be very stable to integrability breaking perturbation, at least if you preserve SU2 symmetry and if you preserve energy, right? So here we only had log, but again, if you preserve energy and you preserve SU2, it really looks extremely stable. And so there are lots of open questions. We don't understand KPZ very well. We don't understand non-perturbative effects, higher order processes in that kinetic equation framework. I'm sure we'll see more experiments coming in the near future. And with this, I'll just thank you very much for your attention, and I can take more questions.
So let's thank Romain. Thank you very much for the nice talk. So yeah, we have some time for a few questions. So people want to ask.
Sorry. So these quasi-particles with size S, and then if I focus on a fixed S, are they just doing diffusion?
No, they move ballistically.
They move, but they scatter with the one with the bigger S.
Yeah. So the one with good. Yeah. So they move ballistically with the velocity that goes as 1/s. And so the one with S going to infinity, they technically only do this anomalous diffusion broadening. Yeah. So yeah, I should say there's a regime. If you actually make if you add some anisotropy, like delta, you take an XXZ chain and you take delta larger than 1, then they actually diffuse instead of anomalously diffuse. Yeah. But yeah, the whole physics really of integrable systems as we understand it now, the hydrodynamics, if you want, is really quasi-particles that move around ballistically. And they have diffusive.
You said they can be screened by a bigger quasi-particle.
That's right. So you can have this screening physics, and otherwise they move ballistically with Brownian motion on top of it. So they kind of do a random bias random walk. Sorry. Yeah.
What does the screening mean?
So the screening really means that they become neutral at long times. The charge, if you want, it's more like their charge is dressed by interactions. And the way this happens is in a dynamical way. So say a magnon has a bare spin 1, but if it's moving and it's flipping sign, effectively actually it ends up having a dressed charge, which is 0. So it's fully screened by an environment, by its environment. And the way it happens is dynamical. in the way we understand, so it takes time before you actually get screened.
I have a potentially naive question. So this characteristic scale of these quasi-particles, I'm guessing there's a distribution of sizes of quasi-particles.
Yeah.
So do you have any data on that size distribution?
Yeah, so we know their density. So their density goes as 1 over s cubed, and we know all the prefactors. So the exact density in the thermal states, we know exactly how they are distributed. So the things we know is we have you can throw away all the quantumness basically, and instead you have kind of a semi-classical gas of those quasi-particles distributed with this density, moving with this velocity, and having this kind of, and they carry some quantum. For each constant quantity you have in your system, like spin, energy, they have like a charge under it. Okay. And on top of it, you have kind of this dressing mechanism. I try to explain in some intuitive way, but yeah. So that's the claim. So we to go back to your question, we know the density.
So I guess what was on my mind is the notion that if these quasi-particles are moving at different velocities ballistically, they will coalesce. That's, I guess, related to that screening mechanism.
Oh, so when they collide, the only thing that happens is basically nothing. They almost don't see each other. I mean, more precisely,
they're solitonic. They just go through.
Yeah, exactly. So they pick up a phase shift, right? So there's kind of there's a Wegener time delay, if you want, when they collide, and that's taken into account in that velocity. So if you want, the velocity itself is kind of dressed by interactions, but they are solitons. Right?
Because
so
the naivety of the question,
they move and they go through.
So the naivety of the question was that your initial configuration was just a jump from one spin to another. So
right.
there was no distribution of initially. So I was trying to work out how the distribution emerges.
Okay, good. So maybe the plot I showed was misleading. So the initial state actually is a thermal state. So it's kind of a jump in the chemical potential, but it's actually at infinite temperature. So if you want, it's not a pure state. It's not like all spin up and all spin down.
Oh, so you're quenching the system essentially.
So yeah, so the initial state is like a density matrix exponential minus mu sz on one side and exponential plus mu sz on the other side. So if you want, it's like infinite temperature with a chemical potential gradient or a field gradient, if you want.
Okay.
Yeah.
Okay, thank you.
Yeah, so for the solitons moving through, you can kind of see it on that plot, right? So if you look at the magnon here, it's moving ballistically, and then it kind of shifts by one side, and then it keeps propagating ballistically, right? So you kind of have like so that's this phase shift, if you want, right? So you kind of have like you have a little displacement, but then everything moves in the same way. Yeah.
Maybe I can make a quick comment related to Ehud's question before. So at least for part of these models, the late time onset of standard diffusion can be recasted in terms of fluctuating hydrodynamics. So the idea is that so the spin 2-point function indeed does have a standard diffusive decay, but then there is a subleading tail which decays faster in time. However, the relative coefficient is very large of this subleading tail. So at the initial times, it looks like the system is not diffusive, and the diffusion constant, that's for the case where the diffusion constant grows logarithmically in time. Yeah, at least, yeah, it does not require energy conservation, but at least it can be recasted in terms of hydrodynamic fluctuations.
Right. So one thing I should say is here, at least for, okay, so the cases you're mentioning are kind of far away from integrability. If you're close to integrability, for us, we don't see log diffusion. We really see this T to the 1/3.
Right.
We also have a log here, but I think it's different from the one you're saying. So because again, it's only close to integrability. Once we go away from integrability, it's pretty clear you saturate as well. Yeah.
Right. Actually, this comment reminded me of something. There is a paper by Achim Roche and Aditi Mitra that actually, they at first thought they saw KPZ transport in a quench of it. There is no SU2 symmetry there. It's just bosons. And indeed, it was in the end that they basically found out that this seeming KPZ behavior was just a subleading term to diffusion that had a very, very large coefficient for some reason. I wonder if in the non-integrable models it's
so
that's
actually,
but here there is a real reason for it.
So I should say, like, there's a whole history here, like, of some other people claim maybe KPZ is entirely stable right away from integrability. Actually, so I guess, Paolo, this is your paper, right? So like, but you had that's pretty much the claim in that paper, that at least far from integrability, this is probably because of those hydro tails, in the same way as in that paper by Akim Hosh and Aditi Mitra and collaborators.
Yeah, what we couldn't explain though is why this coefficient of the subleading term is large.
So it's not controlled by any simple parameters. It's not, you don't know why it's large.
Yeah, it's not clear.
Yeah, so it's kind of a very large parameter for, So I should say here we have a little more control because we're near integrability. If you go very far away from integrability, then it becomes even more mysterious why you would see any of this, right? And then maybe, but I think it's still kind of an open question, right? Like it's maybe some hydro tail, but you need some kind of you need some kind of large parameter that is not, it's not really clear why it should be large, or at least I don't understand why it's large.
Right. If I can still ask another question, is it so in experiments other than transport, is there other measurements that we can see this like quasi-particles?
Yeah, so I mean, so the quasi-particles, you can probe them in many ways. So they control pretty much anything in the system. So they compute they control entanglement growth in the Cardy-Calabrese way. They compute operator spreading. They control operator spreading as well.
So I mean, experimentally, like these
experimentally, okay. Yeah. So experimentally, well, you can measure other conserved quantities, right? So like, so I mean, it depends on the setup, right? So here for spin chains, we're looking at spins or like particle number for like Fermi-Hubbard. If you could measure energy, like you would see like things moving ballistically. Like for other models, so I should say, so this framework of generalized hydrodynamics, it's been applied to say 1D Bose gases. And here you see, ballistic transport of like particles and things like this. So yeah, you could measure like any conserved quantity that you want. If you're focusing on spin, because it's kind of the most, it's the most interesting one, and it's also the most, the most relevant, I would say. But yeah, you could just measure other coordinators.
Okay, thanks.
So if there are no more questions, let's thank Romain again.
Thanks, everyone.
Thank you very much.